Okay, now let's take a look at this table and try to identify one small thing. So as you notice that if we are going to add our two operands, then it really doesn't matter if a is greater than b or a is less than b or a is equal to b. Similarly here, if we are going to add our operands, then it really doesn't matter what you are filling here, meaning a is greater than b, a is less than b, or a is equal to b. If you are going to subtract, then obviously it matters if a is greater than b or b is greater than a, or if a is equal to b. Okay, so keep this in mind while we now start looking at the hardware implementation of this. So before we take a look at the hardware schematic, we are going to worry about, or we are going to designate the plus and minuses using some code so that it is easier for us to do a mux based implementation. So for example, here I am saying that I have the plus sign for a, which is a 0 here, then I have the plus sign for the operation, which means it is the center 0, and then I have the plus sign for operand b, which is a 0. So I am just denoting these the signs of a and b, and I am denoting the operation using a 0 1 kind of a code. For example, what is this? Plus means a 0, this negative means a 1, and this negative means a 1. So which means all these 8 combinations I am representing using a 3-bit binary code. So this 3-bit binary code is telling me what is the actual scenario where what is the value of the operation and what is the sign of the two operands. So for example, the last one is saying minus a, which means the sign of a is 1 meaning negative. I am also subtracting, meaning the center one here is a minus thing, and then b, the sign for it is minus, which means I am going to have a 1 here. So this kind of a code we will use for understanding the muxes that we'll take a look at later on. Okay, now before we look at the hardware implementation, let's determine or decide on something. For example, let's say my operand a is 8 bits. So out of, for example, the 8 bits, the bit location A0 to A6 are denoting the magnitude part, and A7 is denoting the sign of my operand A. Similarly, if I have the 8-bit operand B, then B0 to B6 is denoting the magnitude of the number, and B7 is denoting the sign of the number, which means I can take a look at the value of A7 and figure out if the number is positive or negative. If A7 is equal to 1, then obviously the number A is negative. If A7 is 0, number A is positive. Then also we will assume that someone is telling us through the operation code that if the operation code is 1, meaning I have to subtract A and B. Okay, if operation code is 0, which means I am supposed to add A and B. Okay, but remember that A and B themselves could be either positive or negative, and it is a function of either A7 or B7. So OP is only telling me about the operation that we desire between the two operands. Who will tell that? Possibly the instruction is going to tell us through the opcode. Okay, so as long as we are concerned, we are just saying that 1 bit opcode is going to tell us if we are supposed to subtract the two operands or supposed to add the two operands, and OP is equal to 1, meaning I am supposed to subtract the two operands. Okay. Similarly, let's assume that our final answer is also 8-bit answer. We are adding two 8-bit numbers or subtracting two 8-bit numbers. We'll assume final answer is also 8-bit. Out of those 8 bits, these bits S0 to S6 are the magnitude bits, and then S7 is basically the sign of the final answer. So remember that in our process we have to actually determine the sign of the final answer ourselves through that table. Okay, the magnitude of the final answer we will determine by either adding or subtracting the magnitudes of A and B. Sometimes it is possible that we could also be doing B minus A rather than doing A minus B. Okay, that is a function of the table over there, the table that we saw earlier. Okay, now let's look at the overall schematic. So here I have a 7-bit adder. So the 7-bit adder has two operands X and Y. This is an adder cum subtractor, which means that my carry in, which is referred to as the signal M over here, Okay, if m is equal to 1, I will say that I am going to do x minus y. If m is equal to 0, I am going to do x plus y. This is the sum, which is 7-bit sum, and there is going to be a carry out which I am going to neglect. Okay, this 7-bit answer directly goes as the 7-bit answer or the 7-bit sum that I have starting from S6 to S0. Remember that the sign of the final answer I have to artificially determine based on the table. So here is a mux which is controlled by something here called S7, and this S7's value we are going to control, and we are going to say that S7, will it have a 0 or will it have a 1. If S7 is equal to 1, we are passing a 1, which means we are saying final answer is equal to negative. If S7 is equal to 0, then a 0 will get passed, which means we are choosing or selecting that the final answer's sign digit is equal to a 0, meaning the final answer is positive. Okay. Similarly, here you see that there are two muxes, and these muxes are controlled by something called a swap signal. So if swap signal is equal to 1, then it means that in the operand 1 it is actually passing a B, and in operand 1 over here it is actually passing an A, meaning when swap is equal to 1 it is passing A from here, when swap is equal to 1 it is passing B from here. And if that time m is equal to 1, then I am actually going to do what? B minus A. If swap is equal to 0, then it is simply going to do take A from here, it is going to take B from here, and either I could be doing A plus B or A minus B. Okay, so we'll have to be careful about how we generate our S7, how we generate our swap, and how we generate our M. So remember that in the earlier slide I told you that we are supposed to control these three things through our hardware. We are supposed to select the sign of the final answer. We are supposed to figure out what should I be doing with my two magnitudes that I have. Either I am supposed to add the magnitude or subtract the magnitude, and we have to figure out if I am supposed to swap my operands. Am I supposed to do A minus B, or am I supposed to do B minus A? So to select or generate the values of S7, generate the values of M, and generate the values of the swap signal, we are going to take a look at a mux based design. So here is a mux based design. This is a 2-layer mux based design, meaning the first layer of mux here is controlled. It is obviously an 8 to 1 mux, and here are the select lines S2, S1 and S0. And these select lines are basically controlled by if A is greater than B, A is less than B, and A is equal to B. So how do we find these three things out? We can simply use a ready-made comparator, give it the magnitude of A, give it the magnitude of B, and based on the magnitude we have three binary answers. Either A is greater than B, or A is less than B, or A is equal to B. So remember that these three binary answers are always mutually exclusive, which means if this is a 1, then these two will be a 0. If this is a 1, then these two are going to be a 0, which means that if I give A greater than B as one of the signals, A less than B as one of the select lines, and A is equal to B as one of the select lines, then it means that in this particular mux, the only valid inputs are going to be when only one of the items is a 1. For example, this denotes what? That this input denotes what? This is going to be the input when I have A is equal to B. This is going to be the input when I have what? A is less than B, and this is going to be the input when I have A greater than B. These ones are invalid, this one is also invalid, and this one is also invalid. At any given time only one of these items will be a 1. Okay, all the three cannot be a 0. At least one of them, not at least one, but exactly one of them has to be a 1. It is one hot coded basically. Okay, so this mux is going to basically relate to this table that we have here, and it is relating to if A is greater than B, or if A is less than B, and if A is equal to B. So this mux is capturing that part of the table. Now what should be the remaining part of the table? Remember that in this table we have the first mux that we have placed is talking about a greater than b, or a less than b, or a is equal to b. Now what is the next thing that we need to check? We have covered this. So what is the next thing that we need to check? What is the sign of a, what is the sign of b, and what is the opcode? Okay, so for that we are going to place one more mux. So this is the second level of the mux that we now have. Okay, this level of the mux is going to be controlled by A7 opcode and B7, which means A7 is the sign of operand A. Opcode is telling me if I have to add the two numbers, what is my operation code, if I have to add the two numbers or subtract the two numbers, and B7 is telling me the sign of the second operand. So this mux is going to be controlled by these three items: the sign of the two operands and the operation that we want to perform between the two operands. So remember that now we have something which is a function of the sign of the number, the operand, and the relation of the numbers. If a is greater than b, a is less than b, and a is equal to b. Now what are we supposed to control? So we go back to this. What are we supposed to control? So we are supposed to control the sign of the final answer. So which means we have to generate the sign of the final answer. So in this chart we have to generate this part, we have to generate this part, we have to generate this part, we have to generate this part. This is the sign of the final answer. We have to also figure out what is the operation that has to be performed. Are we supposed to perform addition, or are we supposed to perform subtraction? And do we have to swap our answers, which means do I have to do a minus b, or do I have to do b minus a? So these three items I need to control. So I go back to this chart. In this chart, remember that this is an 8:1 mux, but this is a 3-bit mux, which means 3 bits are entering from here and 3 bits are coming out from here, and these 3 bits are actually corresponding to the 3 things that I have to control. So these 3 bits are corresponding to the 3 items that I need to control. So what are those 3 bits? I have to either control m, meaning I have to subtract or add. So if m is equal to 1, I will subtract. If m is 0, I will add. This signal is actually going to my adder over here, and it is controlling if it is behaving as an adder or it is behaving as a subtractor. Okay, then the second item that I am controlling here, so out of these 3 bits, the center bit is basically the swap bit. Swap bit meaning that this is the swap signal. Okay, if swap signal is 1, I will do b minus a. If swap is equal to 0, I will do a minus b, or a plus b, for example. And then S7. S7 is the sign of the final answer. S7 is the sign of the final answer, and that is basically controlled by S7. If F7 is 1, I am passing a 1. If S7 is 0, I am passing a 0. So the sign of the final answer also we need to generate, okay, based on the table, based on this particular table. So this is the sign of the final answer. Okay. Now let's look at this example here. Okay, so remember that this mux is now connected to which place? It is connected to 100, which means it is connected to whom? It is connected to 100, meaning 100, meaning it is connected to the place where a is greater than b. So now in this table, when a is greater than b, what do we do? So when a is greater than b, and in this mux, when I have the combination 0 0 0, which means now I am referring to this place 0 0 0, which means I have a is greater than b and I have this, then what is the operation that I am supposed to perform? I am supposed to perform a plus b, and the sign of the final answer is plus. And do I need to swap my operands? No. So which means I am going to place over here which 3 bits? I am going to place 0 0 0. And what is the meaning of 0 0 0? This 0 stands for add or subtract, which means I am going to add my answer. Then do I need to swap my answer? No, which means this is a 0. And what is the final answer's sign that you have? S7, it is a 0. So which means this 0 0 0 is corresponding to the first row that I have here. Now let's look at the second row, 0 0 1. So if 0 0 1 is true, and I am currently referring to A greater than B, then what am I supposed to do? I am supposed to subtract the two numbers. Am I supposed to swap my two numbers? No. What is the final answer sign? It is positive. So remember that I have to do A minus B. I am not swapping, and my final answer is a plus. So which means I go back to this diagram. Okay. I am looking at this item. Okay. Then this is a 1. 1 means what? I am supposed to subtract the two numbers. I am supposed to do A minus B. Am I supposed to swap my answers? Meaning, am I supposed to do B minus A? No, I am supposed to do A minus B, which means the swap value over here is a 0. And then what is the final answers sign? What is the final answer sign that I have? It is positive, which means the value of S7, which is this last value, is supposed to be a 0. So this is how we are supposed to look at this particular chart and fill out whatever is required as the inputs to this particular mux. Let's look at one other example. Let's say I am looking at this 1 1 1. Okay, which means in this diagram I am looking at 1 1 1, which means I am doing minus A minus minus B, and currently this item is related to which particular relationship? It is related to this 1 0 0, meaning it is related to A greater than B. So in this table, for A greater than B, for this particular operation, what am I supposed to do? I am supposed to subtract. Am I supposed to swap my operands? No, I am subtracting. And then what is the final answer that I have to choose? Negative answer, which means S7 value has to be a 1. So let's see what happens here. So which means the first item here is subtract related. Second item here is, do I need to swap my answers? Do I need to do B minus A? No, I am supposed to do A minus B. And then the sign of the final answer is a 1, which means my answer is negative. And that is what is the meaning of the 1 0 1 that I have written here. So which means for this mux we have to determine what are the three items that I have chosen. What are these three items? Similarly, for this case, which is this case 0 0 1. 0 0 1 means what? 0 0 0 0 1, meaning A is equal to B. So A is equal to B. For that also you need to figure out what are the inputs that you need here, and these inputs means what? Am I supposed to subtract or add? Am I supposed to swap? Or what is the value of the final answer? Similarly, there will be a mux here connected here. This is for which condition? This is for the condition when A is less than B. There will be a mux here, and you have to figure out what are the inputs to those mux. So remember that if you are taking a look at this mux, which is for A is equal to B, I will be looking at this part. Similarly, if I am talking about the central mux that will go in here, then obviously I have to take a look at this part of my chart from here, and so on. So I have given you an example for the last one, which is basically when A is greater than B. I suggest that you try out on your own what are the inputs to the mux here when A is equal to B and when A is less than B.